Thank you, I think. So, after I've bored you to the point where you are crying with the details of photoionization, I drew you in. I showed you pictures early on and some more pictures. And oh boy, here are a bunch of equations and tables and run scripts and that sort of thing. See, if I'd done that first, that would have been bad. But you do a couple of lectures, one's got pretty pictures, one on black holes, and everybody likes that. And you're not suspecting. You're not suspecting torture. But we're going to untorture you now and go back to looking at it. Cannot, they were very happy I've shown you pictures on the front on the slide here. So, I think I showed you a couple of times that there was a relationship between the mass of the black hole and the mass of stars in the bulge of the galaxy. It's a very linear relationship. It says that they evolve together. But the details of how that works, the physical mechanism, is not very well understood. Now, we can't go back in time or to the early parts of the universe when galaxies were building up and look in detail. They're just too distant. We can't resolve in space what's going on, and they're faint. So that we can't really see what's going on in detail, at least not at this point. So what we do is we look at things in the nearby universe, relatively nearby universe, that we can see what the black hole and its accretion disk and the radiation are doing to the galaxy in a nearby universe, and from that we can maybe understand what's happened early on when galaxies are being built up. So these are sort of like laboratories for us to study the effect nearby, where we can study it, and then we make the inference that this is what happened very early in the history of the universe. At least that's what we tell people. Okay, so these are a number of my collaborators, and just to point out, these two people are Brazilian. She's in there, and then he's a gaúcho from Rio Grande do Sul. And the rest of these people are not. But this is sort of our local group of people working on this in the area. And how do we do this? Well, you've seen this before. This is a Hubble image of a Siever 2 galaxy, NGC 1068. And again, just as I showed you before, this yellowish stuff here, this is gas that's been ionized by the AGN and is moving. I showed you the spectrum of this the other day. The lines were like split, red shifted and blue shifted as the gas moved out. So the black hole accretion disk is down here, and this is all one side. It makes like a cone shape, and that's due to the fact that the molecular torus that I talked about collimates the radiation and makes a nice cone. But the interesting thing is there's a ring out here you can only see very faintly of star formation. The reddish stuff, reddish or sort of red, that's hydrogen recombination lines from a ring of star formation. And somehow these things are connected, and we don't exactly know how, but somehow the interplay between the AGN and the galaxy and either the exciting of star formation or the stopping of star formation are somehow linked. And that's the Hubble Space Telescope. It's looking at this one. These are not to scale, by the way. This is much further away. So, how do we do this? Now, as I said, M87 has appeared again. There are various kinds of AGN outflows, and we talked about radio galaxies and radio loud objects, and they have these extremely powerful relativistic jets. Here's a radio map from the Very Large Array of M87, one of the famous black hole interferometric image, and that's down in here. And these things are very powerful, but it's not immediately obvious how a jet would clear out the gas. So let me go back one step again. There are a number of stars in the bulge is correlated with the mass of the black hole. Black hole must be built up over time by accreting mass. The mass that is in the bulge forms stars. Something turned off the star formation and stopped the increase in mass of the black hole. Some event stopped them at the same point. And so one of those things could be a jet. Jets are extremely powerful. The particles going at relativistic speeds. We see them impacting the galaxy, but there's two problems with jets. One is, you can see it right there. You're inside a bulge of a galaxy, and here you have this very powerful but very narrow collimation. So anything in the way here gets pushed out, but all the stuff over here is not affected. There are ways people think you can do that, but it's rather a complicated hydrodynamic model that does it, and it's not sure whether it really works or not. The other thing is, they're not that common. Only about 10% of active galaxies are powerful enough and have these jets. But all active galaxies show the emission lines that I've been showing you. So the ultraviolet and X-ray radiation from the accretion disk is there all the time, ionizing and accelerating the gas around the center parts of the galaxy. But the jets occur very rarely. So it's important, but probably it's something more in the form of AGN winds. So we talked about photoionization, the ionization of gas. In addition to ionizing gas, the photons that are absorbed by clouds of gas around the nucleus of these galaxies are accelerated by radiation pressure. So the photons are going in one direction, which is out from the center, and the gas gets pushed by the photons. And so that sort of thing, radiative acceleration, can be very important. But in any case, it makes winds. There are other ways to make winds, which I'll get to later. And even in local galaxies, these winds can go a couple thousand kilometers a second. So if there's enough gas in the wind going at that velocity, it can deposit a lot of kinetic energy or momentum into the gas around the nucleus. And unlike the jets, it has a wide opening angle. Even though the thing that I showed you before has a cone-like shape, it's not narrow, narrow, narrow like this. And so one of the ways we can go, and again, these can go up to 10% the speed of light in certain types of quasars. And so one of the things we can look at first are absorption along our line of sight, or the extended regions, the narrow line region. Look at outflows in the nearby Seyfert galaxies and understand the physical mechanism of how that might work. And then we can apply that knowledge to more powerful objects, which we can't see in so much detail. Now, absorption lines, I showed you some absorption line spectra the other day, and gas that is in line of sight to the accretion disk, that gas absorbs radiation and produces absorption features. If the gas is moving, the absorption lines are shifted, say if it's moving out, to the blue. And so the amount of that shift tells you how fast that gas is going. If you can determine the amount of gas that's producing that absorption, you know how fast it's going, you can get kinetic energy. Well, actually, we really look at the rate that kinetic energy is deposited, but the same idea. So, there we go. So what evidence do we have for winds from absorption systems? Well, we've known about this for some time, a couple of maybe 20 years. And basically you see, this is a carbon-4 emission line. This is the emission line here from the broad line region. And you can see it's a little bit, irregular here, but here there are pieces of it that are missing. This is what the rest velocity of the emission line is. So if it was just random motion, it'd be perfectly symmetric, a Gaussian-like shape around that point. If there wasn't outflow, you'd see some stuff here. But all this is blueward. You can see it's in velocity here of the center of the line. So this is all stuff that's coming out of this particular Seyfert galaxy. This is with Hubble. This is a FUSE, which is a now defunct far ultraviolet spectrograph. And Chandra, which is the Xray one. This is done with the high energy transmission gratings, high X-ray resolution. And you can see the resolution isn't as good as in the Hubble, but you can see the same sort of shape in this oxygen 7 absorption as you do in the carbon 4 absorption. Yes?
Are all those dips, for example, in the top spectrum is carbon 4 with different velocity components?
Yeah. Carbon 4 is a doublet though. So for each velocity component you get 2 lines. That's what brackets are. That's one. There's one faint one there and there. There's one here, and there. They line up. So yeah.
So why do you get all these components of different velocities?
That's an interesting question. Talk about it.
Basically.
I mean, why wouldn't you? Okay, so, and then, again, you can't see it as well in oxygen 7, so it's sort of wiped out. These X-ray ones are traditionally called warm absorbers for historic reasons. So if you see that term, that's what it means. But it's just higher ionization lines. This is helium-like and hydrogen-like oxygen. And these things are moving at velocities very similar to the gas that's moving, that you see in the ultraviolet. And actually, just to answer your question, there are several, this can be seen as a bunch of different shells of absorption. The different shells of absorption don't have to have the same velocity. So these individual components are all along our same line of sight, but they're not necessarily at the same velocity or the same distance. So if you look at that thing, if you can look at the structure that I showed you for the narrow line spectra, there were a series of knots and clumps. It wasn't one continuous flow. And it's not a continuous flow here. So again, why study winds in Seyfert galaxies? Basically, they're radio quiet, which is the more common phenomenon. And again, this is an important thing in terms of galaxy evolution. These guys are nearby. This is redshift of 0.1, which is 300 megaparsecs. And so they're very bright. You can look at the detailed physics. You can resolve the nearby ones. So you, like I showed you the other day with Hubble. And then if these winds are important at these luminosities, then they would be even more important with quasars, which are 1,000 times more luminous. So if there's enough radiation in Seyfert galaxies to make these flows that affect the evolution of the bulge, then if your quasar is 1,000 times more luminous, it should be better at it. And, you know, so that's the rationale. You look at the things that are nearby that you can study in detail. And the question then is, what are the absorbers? And this goes back to your question a bit, Rhonda. Where do they come from? We can see there's gas between the source of the radiation, the accretion disk, and its corona, and us. We can see that it's moving outwards because the absorption is shifted to blue. But where did it come from? Well, there's a lot of anywhere. To be honest with you, anywhere where there's gas. It could be the outer parts of the accretion disk. It could be the broad-line clouds of the cells. It could be that molecular torus that was in that weird picture that I showed you from Antonucci's article. It could be the narrow-line region. It could be other stuff from the disk way further out in the host galaxy. The problem is, if you're looking in a straight line towards the center, it's very hard to tell what the distance is. If you're looking at it in the opposite sense and have it spatially resolved, you can tell what the distances are. But if it's line of sight, then you cannot directly tell the distances. There are ways to get at it, but it's difficult. The question is, how are they accelerated? Obviously, they're not at zero. They must be accelerated at some velocity. And so I talked about radiation. And that would be a simple way to do it. There are other things that you can look at to do that. One is thermal winds. So if you make gas hot enough, it'll expand. And it expands along density gradients. So it goes from the dense regions to the less dense regions. And there was some thought that if you heated up something like this torus, this molecular torus, you could have a thermally expanding wind. It probably isn't the case. Oh, by the way, just for historical reasons, that was what people initially thought the solar wind was from our sun, back in the models that Parker made back in the 1950s with thermal winds. It turns out that in very many contexts, thermal winds are not very efficient means to make, or thermal expansion is not a very efficient way to make winds. And then hydrodynamic winds, or hydrodynamic flows. These are interesting, but you need to have a very strong magnetic field. It's basically a plasma physics calculation, and the material can be accelerated along open magnetic field lines. And you get to very high velocities if you have a source for energy that will get them to those high velocities. Well, there is one, and that's the accretion disk. The accretion disk is ionized, so it's threaded with magnetic field lines, and we know that has to be involved in radio jets. So that has to be a magnetohydrodynamic flow. Because the jets, they're going at 0.99 times the speed of light, and they're very highly ionized. Radiation wouldn't work, so there must be the emission is synchrotron, so they must be magnetic. So magnetic and radiatively driven both could work. Thermal winds have been proposed, but probably don't work. And then there are accretionist winds, evaporation force, I say, and where are they? Well, it depends on where they came from. If you're down here, you are, light days or less. This is like, 5 to 100 light days away. Typical Seyfert galaxy, this is a half a parsec to a parsec. This tens to hundreds to 1,000 parsecs. So the distance depends on where it came from. And how do you get the distance? And that's another thing. First, you got to measure stuff. The way you can get distances is if you know the density. So if you remember the ionization parameter, which I will not bore you with again, it is a measure of the relative ionization of the gas that you're modeling. And basically, it's a function of how much in ionizing photons the source can produce, diluted by a distance factor of 4 pi r squared, and the density of the gas. But if the source goes up and down in ionization, the ionization parameter goes up and down. I showed you the variability in that X-ray spectrum. I think I showed it to you twice already. And here's an ultraviolet spectrum of NGC 4151 taken over various epochs, and you can see things are going up and down. I mean, this is very, very deeply absorbed, but the absorption changes, and the profile of this is the broad emission line, this piece missing due to absorption goes up and down. So if you can measure the ionic columns, I told you a little bit about that, you get an optical depth theorem from that. You can determine by the properties of the transition how much gas has to be there to produce that sort of optical depth. And our friend, the photoionization models, you get the ionization parameter. This is the column density. We talked about that. Variable ionization, you get the recombination time. Within the mess of equations I showed you yesterday, there was one that showed you what the recombination times were. So it's a function of the density and the recombination coefficient. So if you see how they vary over time, you can figure out how dense they are. You plug that all back into the equation for ionization parameter, and you get the location. Easy. The problem here is this junk. If the line is so deep and saturated, it doesn't vary enough to get anything useful. And here's absorbers that show various variable column densities in another source. This is a little easier to manage than 4151. This is 3783, which doesn't have as complex absorption. And so we live in a galaxy, and there's gas in our galaxy, and this is galactic absorption. That's just local to us. It's blue shifted. The reason is the universe is expanding. So this galaxy is red shifted, so the galactic carbon-4 absorption here is all shifted to the blue. You can see the doublets. And at this point, in 1993, there was no absorption. And then later, these things showed up. I don't know why 2 came before 1. It's somebody else's problem. And then another one showed up, and then even more components showed up. So why is this happening? Well, they're different components, but they come and go either because they're ionized or recombined so they don't produce this emission, or what is equally or perhaps more likely is the motion of these things is not strictly, we would say, radial. So not just being pushed away. If it came off a rotating body, like an accretion disk, it has azimuthal velocity as well as some radial velocity. So instead of going straight out, it goes out in a helical pattern. And so that would produce this coming and going of these components. And there's a picture of it from a paper that Crenshaw and I did. And this is coming from some disk thing, so it has both azimuthal and theta and radial components of velocity. And you can see as it evolves, it follows that kind of a pattern. And so you can do this for a set of conditions, the origin, the angle with which you're looking at. You get the velocity in the line of sight that you can measure. And if you assume that this component is 0, so it doesn't have a theta component, but just a phi and an r component, then you get a phi, or a transverse velocity, of 2,100 kilometers a second in this particular case. There's also one at 10,000 kilometers. It's actually shown on this. I think it's this guy. This is the 1 centimeter. And so just because it's spinning around as it's pushed out, it goes in and out of your line of sight. That means maybe it's coming from a disk, or a disk-like thing. So we did a bit more with that, and based on what we could find out, based on the density and the ionization parameter and such, it looks like most of these absorbers that we see come from somewhere between the broadline region, so maybe 100 light days out, to the inner parts of the narrowline region, so tens of parsecs, that scale. So that region seems to be where this stuff comes from. And yes, there are lots of arrows pointing which way and the other. The open ones are UV points, the dark ones are X-ray points. And you can see this is a log of the distance over parsecs here. And so here's some stuff at about 100 parsecs, and here's 1/100th of a parsec. So it's all grouped in this particular region. So the accretion disk is down in here, and there are only a couple of points that look like they originate that far deeper. And then if you go out here, you're starting to lose points, but that may be because that gas is so far away it's not effectively accelerating. Because you have to remember that you have the radiation that's pushing you out, gravity is pulling you back. If you're close to the disk and the black hole, it's only the mass of the black hole that's producing that gravity. But if you're 100 parsecs out, there are lots of stars. So the enclosed mass gets bigger and bigger, so your gravitational deceleration becomes more and more important, at the same time as your radiation is more and more diluted by the 1/r² factor. So as you go further and further out, it's much less and less and less efficient to drive the flow. And that's kind of what this tells you.
So Steve, just a curiosity, is it anything that those who are very small distances are actually measurable? Could be just a fluctuation, like 2 dots.
I wouldn't worry about those 2 dots. You can see they're kind of divvied up here pretty well. I'm not exactly sure what these guys are. I mean, they're very low velocity, so they're probably not very interested in terms of outflows anyhow. There is one reason why that might be, but it's a rather complicated answer, which I'll talk about later. It's what you're looking at seeing absorbed. So if you're looking in the UV, you're looking at absorption of an emission line. The X-ray could just absorb the continuum. But if you're in the UV, you might not be able to detect that quite as easily. Okay. So now we talk about the whole process. I might not have used this word, but this whole process is called AGN feedback. So it's a feedback mechanism. Somehow the fueling of the black hole, its increase in mass, and the eventual stopping of star formation by the outflows is some kind of feedback mechanism. And the source of the feedback in this case are the winds that are accelerated by the atom nucleus. No more photoionization models yet, and radio locations, and then the important thing here is you want to know what the dynamic impact of these winds are on the host galaxy. So to do that, you need the map, you have the velocities, but you need the total masses, and you need the mass outflow rates, and that's denoted by this little formula here. This is a column density, and this thing here, this is the mass of the proton. The velocities you measure, this is the thing that's hard to do. This is a covering factor. And so if you want the total mass, you have to know how much of the nucleus is covered by this material. If you're just looking along your line of sight, it's like this piece. So how much of it is it really encompassing? Because your total mass and your total mass outflow depend on how much material you have, and you're only looking at one line through, you can't tell. So they say that 50% of active galaxies show this kind of absorption. So the covering factor must be on average statistically 50%. So they said this is 0.5. Whether that's really good or not is another issue. But here's the real important thing here. This is a kinetic luminosity. So it's just like kinetic energy, but replace M with dm dt. And this is the dm dt. And this is the rate at which kinetic energy is being deposited into the host galaxy. So if this is sufficient, then you can probably quench the stop star formation. And by the way, this number is always way bigger than this number, which is the mass that you need to accumulate to power the AGN. So the powering of the active galaxy by mass accretion is so efficient that you only need a tiny fraction of that to make these very massive winds. And so here's, you can also look at this in terms of the accretion rate versus the outflow rate, just to illustrate what I said. You can see it's thousands of times or hundreds of times more typically, except in this particular case where it's really unknown. And so again, we think of gases outside the accretion disk, and they're not necessarily accretion disk winds, although these things, UFOs, which I'll talk about in a bit, are probably accretion disk winds. Almost have to be. The other thing is you can look at the kinetic energy versus the volumetric, kinetic luminosity versus the volumetric luminosity. That's all the radiation emitted by the accretion disk overall, the entire electromagnetic spectrum. And models say if the kinetic luminosity is about a few percent of the volumetric luminosity, that's enough energy being deposited into the bulge of the host galaxy for feedback. These also could be important in moderate luminosity AGN, but they may not be affected at low luminosities because this sort of relationship starts breaking down if the volumetric luminosity is extremely low. So yeah, you could be 5% volumetric luminosity, but if it's a very weak source, that's not enough energy to do anything. So how do we do this? We can go look at the narrow line region, though. That's a little easier to deal with because you know the distances. And here's, again, we like NGC 4151, it's nearby, and we can look at it. And this is an O3 image of 4151. There's the scale here. This whole region is probably about 200 parsecs on the side from the center. And out here, you're getting about to the region where star formation could be important in the bulge. So if you get out to a kiloparsec, that could show you that if you had winds that were affecting the bulge and stopping star formation. The way you model outflows, my colleague Crenshaw at Georgia State, this is the thing he does, and his students do this, but what we do is we have, in this case, we have long slit spectra that shows you the position of the spectra. From that, we measure the velocities as a function of position, and then if you think you know the geometry of this region, and you know the orientation of that geometry with the disk of a host galaxy, because this is a spiral galaxy with a disk, you can see, if you understand the deprojected velocities and how much outflow you're getting. Remember, the velocities you measure, you're not in the narrow line region, are not in your line of sight, so you have to deproject them to get the velocities. This is what you get. This kind of double peak pattern with the nucleus right there is typical. And I forget what the red and the blue points mean. I think in this one, it's not the velocity, because you can see this is positive velocity, this is negative velocity, it's because of the shape. In this case, you're not looking at line of sight, so stuff coming out of the nucleus can be going away from you. But I think it's something to do with the line profiles that you fit, and bad choice of colors. But here's the interesting thing, is that, I think this was asked the other day, are these things aligned with the disk of the host galaxy? In this case, this is your bicone here, and this is the disk of the host galaxy, and they're not aligned at all. And that is the typical case. And again, we go through 4151, you do long slit spectra, photo-ionization models, that gets you the physical properties of it, and all these other things. You can extend your calculation outside the slit if you're clever about it, and you get the total mass. I'm not going to go through this in any detail. This is rather a complicated process. Not complicated, but there are a lot of steps. And finally, you get a mass profile. And there is the mass outflow profile of NGC 4151. And so the thing here is, if you just look at the center and assume that that was going to produce all the mass, this is how your mass outflow rate would evolve over distance. So you look at the very center and say, I've got this tiny amount of mass, I'm going to let this go out further and further and further. Over time, this is what you get. But if you do the calculation based on the spectra that we had of what the mass outflow rate really is, it looks like this. And so there's one point where it's peaking at over 2 solar masses a year. So it's a rather significant outflow rate. So the thing is, this gas can't have come from here. It has to have been out here already. because the flux of gas is too low from the center region. And so that gas is gas. I think I showed you a picture of that cartoon from Fisher of these dust spirals going in. That's the origin of a lot of the gas in these outflows, are these dust spirals that cross into the cone of illumination that the active galaxy produces. And then that's where all this junk comes from. But eventually you start losing the efficiency of the outflows. The kinetic luminosity is about 0.4% of voltmetric. It's a little bit misleading here because this source is so weak. This really isn't enough energy, even though it makes that percentage criteria almost. You have to. That only works really for more powerful sources. So here's another thing, a similar analysis on another Seyfert galaxy, a much more luminous one, Markarian 573, but the same kind of analysis is done here with the pretty pictures that Crenshaw likes to make. You can see here that the Bicone is embedded or by the plane of the host galaxy, unlike the other one. And that means you have a lot more material in these dust spirals that go through the disk that you can drive. And these are completely pointed out, it's a very inefficient process. If the disk is like this and your cone's going like that, your radiation isn't hitting anything, except the stuff really close by. And the stuff close by doesn't produce much, as I showed you in the previous plot. But again, the same sort of pattern of behavior exists. But there's also weird stuff going on out here. And here's a picture. This is a structure map. So it shows you dust lanes that are going through the center of this galaxy with this cone here superimposed on that. And you can see how these dust lanes are showing up. They happen to be the white things in this particular spread, are showing up inside the cone, the accelerator. But there's odd stuff going out here, and I'll talk about that in a second. So, as I said, Seyfert galaxies are nice because they're nearby, but they're not very powerful. And so they really can't do this very efficiently. So we went up to the next level of luminosity, and these are type 2, so they follow the unified model, AGN, but they're quasars. So they're hundreds of times more powerful than the Seyfert galaxies. And we had a program with Hubble to look at about 12 of these. And here are the spectrum. So these are spectra taken with a medium resolution spectrograph. So it centers down just on a couple of emission lines. These happen to be emission lines of oxygen. So the oxygen doublet, although sometimes with redshift problems you only hit one of them, because the other one's over here somewhere. And the reason you want to go to higher resolution is you can spread the line out more, dispersion, and measure the velocity more accurately. And so for modeling these things, we really would, kinematic analysis, you want as high resolution this way as possible. It's a bit of a problem because you don't have a lot of emission lines. How you do photoionization models with like 2 or 3 emission lines, but there are ways if you have other photoionization models you've run, then you don't need that many lines to at least infer what the column densities and densities are for these things. Are doing that. But basically you can see some of these things are really spread out. Some are not so spread out this way in dispersion. Some are spread out this way in terms of spatial. And this tells you something about that you weren't expecting to see necessarily, which is mass outflows evolve. Not in our human lifetime from one object, but from one object to another object. And so these things were more like the Seyfert galaxies, the 1068 and NGC 4150 one I showed you, where you have extended outflows in the narrow line region, shifted to the blue on one side and the red on the other side, as the thing's going this way and that on the other side of the disk going the opposite direction. But some of these things like this, they're very, very smeared out. What we think is it's in an early stage. Remember I told you that it's not just the unified model, it's an evolution. So early on, there's a lot of gas that's accumulated in the central potential of these things. When you turn the AGN on, the first thing is it creates winds that tries to push that gas out. As it pushes that gas out, you get shocks occurring, all kinds of turbulent activity, and that, we think, is what's producing this. So they're not going very fast, but they are very disturbed. As the galaxy evolves, you go from something that looks like this to something that looks more like this. as the stuff in the inner part is cleared out, and you start getting the flows occurring more out into the narrow line region. And so that was something we weren't expecting to see, which is sort of interesting. Here's a close-up of Markarian 34, which is the nearest of those Quasar 2s and the brightest. This is an image done in Oxygen 3, taken with Hubble. This is a Sloan image. This is on a higher scale. This was used to figure out what the orientation of the host galaxy disk was. And these are the slits that were used for this. This is from a paper by Travis Fisher in 2018. You can see some of the same patterns, the different slits. This is a flux thing, it's not all that interesting. But what you can see here is that you have some high velocities, but you also have some very high full width half maximum. That's that spreading of the line. And sometimes you get higher full width half maximum at fairly large distances, higher than the velocities you see. It's not so much evident in this one, but some of the other ones show that. What we think is happening there is that these winds that are generated from closer in reach a region that's too far away for them to accelerate, either by pushing it or having that gas accelerated by radiation. So the winds just push up against denser structures, and that causes them to splay out this way, and you get a very large full width half maximum. So Fisher calls that disturbed kinematics. That may be a very important point, because that may be the mechanism that you stop star formation, or start star formation. But it shows you a kind of interaction between the AGN winds and the host galaxy. Trouble with this is, even for these more luminous ones, it doesn't really work all that well. A bulge of a galaxy is like, 3 to 5 kiloparsecs. Maybe 3 in radius. We don't see winds getting out that far. We get them, say, maybe half a kiloparsec or a kiloparsec, and then either by the dilution of the radiation or the enclosed mass, the winds don't go any further, so they don't look like they're going to clear things out. Here's a paper by Mitchell Rowalski on Markarian 34, and you can see stuff, the outflow rates maybe about a kiloparsec, this is minus 1,000 parsecs out, and then they die off. And here's a comparison of 4151, which is in black, Markarian 34, which is in blue, and I think Markarian 573 might be in some other color. All right, both. This is gray and black. So this is 4151, which is not a very powerful one. Everything happens close in. Markarian 573 is more powerful. Things get a little further out. And then Markarian 34, which is a quasar, things get a little further out. But they don't go far enough. After you get past about a kiloparsec here, things die off. This shows you all the different things: kinetic energy deposited, mass outflow rates, mass profile, momentum. It's just not depositing energy at large enough distances. But we're only tracing one sort of general type of gas. We're tracing gas that's emitting optical emission lines. And we know there's a lot of other stuff there, because when we look in the line of sight to these things, you see X-ray absorption as well as ultraviolet absorption. So what about the X-ray? Well, this is from a paper that it's me. It's at the journal right now, and I'm fighting with the referee over statistics. But this is a Chandra ASIS HETG spectral image of NGC 4151 again. It shows you very highly ionized emission lines, helium and hydrogen like oxygen, helium and hydrogen like neon, helium and hydrogen like magnesium. That's a K line close in. Helium and hydrogen like silicon is another K line. These K lines are formed in the torus, and these are, this point spread function of Chandra is not that great, but this is very symmetric and centered at the center, so it's probably unresolved close in. But clearly this stuff is all resolved and shows extent, and that extent goes along the same way as the optical gas. So living with the optical emission line gas are X-rays traced by these things. And so what you can do is you can go back and do a bunch of photoionization models if you want, and figure out again what the masses and mass outflow rates of the X-ray gas are. So that's what I did. And so I could compare those to the optical and UV ones that Crenshaw and I did before. And you can see this is in thousands of solar mass. There's a considerable amount of mass here, like, regions of like 10 to the 5 solar masses. The red points are the optical and the black points are the X-ray. We only got an upper limit in this outer bin because the bin size wasn't very big compared to the X-ray bin. But it's probably on the same order. More interestingly, you can see what's happening here. The optical stuff, you have some peak outflow, and then boom, it's coming down again. With the X-ray, it looks, again, this is based on an assumption about how the density of the gas goes, it looks like the X-ray continues out. And so they're on the same comparable order in mass and in mass outflow rate, so the kinetic energies they're going to deposit are comparable. But it looks like the X-ray gas can get further out. How can that happen? Well, it happens because these things are hot, and hot stuff expands. So now we're back to the thermal idea, but we're not making thermal winds. So it may well be that the source of this X-ray gas is gas closer in that you would see emitting oxygen-3 and other things like that. But that gas will expand at its sound speed, unless there's some confinement mechanism. And as it expands, it's more rarefied, lower density, so with the same radiation, it gets more and more ionized. And that stuff will continue to flow. So it may be that the source of the X-ray here is from a pool of lower ionization gas. We kind of know that because the oxygen-3 gas comes from molecular gas that goes into the illumination cone. So you start out with molecular gas, you ionize it, you get dissociate it and ionize it, you get oxygen-3, and then as it evolves and expands, you get X-rays. So it may be we're missing, by looking at oxygen-3, the major component. This is a low luminosity Seyfert galaxy, and here they're comparable. It may be at much higher luminosity, you could get much higher components of X-ray.
So serious that you still feel that you're strong with X-ray gas?
Nope. This is a photoionization model of emission line gas. And this stuff is generally a few times 10 to the 5 Kelvin. So it's purely an emission line source. But there's more. So optical stuff, well, it's doing maybe something interesting. X-rays, that might be more interesting. It might be a better source for feedback. But there's one other thing. Is that okay? That's UFOs. UFOs are the fault of Francesco Tombesi. What it stands for is ultra-fast outflows. It's one of those guys that thinks up cool titles for things, which he's used to get papers in Nature. He's a good guy. He's a colleague of mine, but I would never have thought of that. Just wouldn't have. So basically, the X-ray winds I was showing you in the ultraviolet gas, like from the first image I showed you that showed the Chandra, the Fuse, and the Hubble together, they're all like 1,000 kilometers a second, roughly. These UFOs can get velocities up to 0.2 times the speed of light. All right? Hence, they're ultra fast. Remember, the kinetic energy is 1/2 mv squared, but the kinetic luminosity goes as v cubed because you have a time change in mass at the MDT. So as you get faster and faster, you have more and more kinetic luminosity. So these things, if they go far out, will dominate the dynamics of outflows. And obviously I like NGC 4151. Here's one of NGC 4151. And this is XMM and Suzaku spectra showing the, actually this is just XMM, showing this feature here. And this is shifted iron, it's iron 26, hydrogen-like iron, shifted to about 0.1 C. And this dispersion here, the only thing, some of these things are hard to pick out, but the dispersion is big enough that you can see it's a real feature, and you can look at this thing about the significance of the feature, and it is quite significant. And the fact that it's spread out means that it's a large velocity gradient along our line of sight. So like in the UV, as Robert was asking, you see different components at different velocities. Here, there's probably components at different velocities, but at this resolution, it just looks like one thing that's spread out. So if this thing gets out, it's going to have some major effect. Again, HC 4151 is a fairly weak Seyfert galaxy. It just happens to be nearby. But if you look at other things, there are much more dramatic UFOs. This is PDS 456, and from a paper by Gaspari et al., and just in Sierra, by the way. And these are data showing all these absorption features of iron. And he's nicely put the velocity. So he's got iron 25 in emission. He's got iron 25 beta at 0.24 C, iron 26 Lyman beta at 0.24 C, 25 alpha at 0.2 C, 0.24 C. This one also shows a lot of other absorption lines shifted to these very high velocities. This is a quasar, so it can accelerate a lot of this material. If this stuff gets out there, it has very high kinetic luminosity. So these UFOs could really be the thing that drives feedback. So it's interesting, you start out by looking at the optical and UV emission and absorption, and that's one piece of it, and then it's interesting, but it doesn't go very far. Then we look at the X-ray lines, the hydrogen, helium, light, oxygen, and neon lines, and we see there's a lot of that stuff that we haven't thought of before. We also find out that even at large distances, even though we don't have optical outflows, the gas is disturbed, which suggests something is doing something to it. One possibility is that more highly ionized gas is hitting it, because we see the effect in those quasar 2s with a very high full width half maximum close in, where winds or something must be hitting that gas and causing it to be so disturbed. So we see that at larger distances as well. And then, if you really have one of these things, it has very high kinetic luminosity, much more so than the X-ray gas, and these things can drive outflows. The problem is it's very high. Very highly ionized and not very stable. So where is it and how far does it get? This is an absorption line study. You can't tell from that where it is. So in order to get these, you got to go back to photoionization models of things you know about. And so there's a bunch of them that Pombesi had, not PDS 456, but more which is quasars, more Seyferts. And so we looked at the iron 25 and 26 in those, and figured out what possibly their maximum radial distances are. This is a trick in photoionization modeling. This is a very rough upper limit. The thing can't be thicker than its distance to the source. So you can set that as a rough upper limit. And then you can go through and figure out, based on photoionization models, where this stuff is and how much stuff you've got. And what we found out initially, though, was there's some peculiarities about this stuff. First off, the column densities you have to have. Remember I was talking about 10 to the 23 being a big column density? And 10 to the 24 is pushing the point where the thing is thick to electron scattering. These are getting close to 10 to the 24. So in order to produce any of this absorption, you have to have a very, very large amount of gas, which is good because if you want feedback, your M is very big and your velocity is going 2c, so that works. It turns out, interestingly enough, that there are things that are not UFOs that produce iron absorption, and they seem to have fairly low columns compared to the ones that do produce the UFOs. But this is kind of interesting here to those that like it. I'm not going to go in detail what this is, but you can use this to determine what range of heating and cooling mechanisms there are in the gas, whether it's stable or not. I talked about heating and cooling from emission lines, heating by ionization, cooling by emission lines. If you are very highly ionized, that doesn't work anymore. What happens is everything is done by Compton processes. So you Compton scatter radiation in, and you inverse Compton and you Compton scatter radiation out. And this is the Compton part, this range. And all these guys, these UFO guys, are all in Compton range. And that means their temperatures, you can see this is in Bob, are like about 3 times 10 to the 7 Kelvin. Absorbers we see, and these are the iron 25 and 26 absorbers that are not UFOs, who seem to be on an unstable part of this curve. So maybe they go up here sometimes and pop down there sometimes. In that part, any perturbance drives you one way or the other on this particular stability curve. So these things are very hot. That's a problem. just like the O3 gas is hot and expands and makes X-ray gas, if this expands, what does it make? Like nothing. It just becomes a very, very tenuous thing. And so how far can something get that's a 10 to the 7 before it expands into nothingness? Not very far, unless something else is going on. The other thing about these guys is that they're basically only iron and nickel have any electrons left. Everything else is completely ionized. So it's a sea of electrons with a couple of heavy elements with an electron or two attached. That means this can't be accelerated by radiation, because it's almost all Thomson scatter. So what accelerates it? The other thing is, it could be accelerated if the sources were radiating at Eddington. So that's the limit. But if they're not radiating at Eddington, then you don't have enough radiation to accelerate something that ionized. And these sources are no more than 30%, and a lot of them are less. And it doesn't scale with the velocity of the outflow. So it doesn't look like radiation is part of this. And so, if that's true, this is a force multiplier. This basically means that the thing is stripped of all bound electrons. And this lack of correlation suggests these are magnetic. And we did a treatment, a MHD treatment on these things and showed you could get them these velocities. It's a rather detailed analysis, but basically the idea is these come from the accretion disk. The accretion disk is threaded with magnetic field lines. That's what makes jets. But one step less than a jet is making a UFO. So you don't make relativistic electrons going 0.99 C, but you make gas with very highly ionized, but with some iron atoms with some electrons in it, going at 0.1 or 0.2 C. And basically what happens is you translate the rotational speed of the disk, which can be a fraction of the speed of light close in to the least stable orbit on an accretion disk. And that material can go out along open field lines. Kind of like if you have a thing with a wire on it, you put a bead on the wire and swing it around, the bead goes out the wire. And so this is called a cold magnetohydrodynamic process. Cold being that the magnetic pressure dominates over the gas or radiation pressure. And with that, you can get these things at very high velocities without photoionization or photoacceleration being involved at all. The problem with that is you have to be really, really close in. Remember, the other absorbers were not that close in, and of course the narrow-line stuff is tens of hundreds of parsecs away. So yes, you have a source that can accelerate them to those high velocities, but what keeps them together to get out to the narrow-line region? Well, it depends. I mean, if there is some kind of confinement process, maybe you could do it, and maybe there is some magnetic confinement. So if there's some magnetic pressure associated with these things, then maybe that'll keep them from expanding thermally and gets them far enough out to have some major effect on the evolution of the bulge. So they may be really important if they can get out kiloparsec scale. Otherwise, they're interesting but not that important, even though they got a fun name. So here's a nice picture from a former student, Juliana Couto, another Brazilian, from her thesis showing the structure of this region. So here's your angle of your observer. This is not exactly to scale, but this is the molecular torus out here. Here's the accretion disk in the black hole, the torus being about half a parsec out of this source. Here's the X-ray corona, the broadline region of these little dots. And here's the UFO based on this. It has to be that close in to originate with a strong magnetic force. These are normal X-ray and UV absorbers going further out. You can kind of see what the scale is. And so these may get fairly far out, but how this one can actually get out without completely becoming super tenuous, we don't know. It turns out these absorbers, these UV absorbers, are easily driven by radiation. These could be, maybe not. These are very high ionization X-ray absorbers, but they show up as things like hydrogen, light, oxygen, and neon in the X-ray spectrum. So in a more luminous source that can be radiatively driven, maybe not in this guy. UFOs clearly can't be. So If these get out here, then you have feedback. So, some quick conclusions. We have UV and X-ray absorbers out to about 1 kiloparsecs. The mass outflow rate is very much bigger than the accretion rate. This doesn't really mean much, except it tells you that the mass accretion is extremely efficient about producing energy. But most of the outflow originates outside the accretion disk, and inflowing glass gets blown out. So it's we call in situ acceleration. It was out there in the disk when the AGN started accelerating. Kinetic luminosities can be fairly high in terms of the limits by models, but again, this depends on what kind of source. The volumetric is very low. It doesn't matter whether the kinetic luminosity is 5% of the volumetric. If the volumetric luminosity is close to the maximum that the source can radiate, then 5% is important. But in any case, they could provide feedback. The problem with this, in these two bullets, is they don't show a large enough extent to clear the bulges. So if you look at the optical and UV outflows, they just don't get far enough. So what are the answers? Answers could be X-rays, and then what is the role of the UFOs? Something that we're not, if it works, something that we're not really looking at is doing the job. And so that's where I'm going to leave it. So it's kind of an open thing. We keep getting a little further and a little further and a little further in this process and say, look, that's interesting, but that's not it. This is intriguing, but that's not it either. And we keep going incrementally by eliminating things, and eventually we may find out that AGN feedback doesn't work at all. I am optimistic that something in the X-ray, the UFOs or the X-ray winds I was talking about earlier, are really what's doing it. And the other thing is that when we talk about AGN feedback, the simplistic idea is the AGN turns on and blows all the gas out and star formation stops. But I don't think that's the case. And one of the sources, one of the QSO2 sources that I skimmed through that shows the very high full width half maximum, so the O3 very close in, has a extremely powerful starburst in its inner 200 parsecs. And so one of the things that happen is not feedback. This is called negative feedback when you stop star formation, but positive feedback. So the winds interact with the molecular gas in the disk, and they start a massive burst of star formation. And then it's not the AGNs that clear the gas out, it's the stellar winds and the supernovae from the positively induced process that's doing it. But again, we're getting incrementally closer, but we're not there yet. So there's work to be done, and that's it.